So I want to walk through a full example of taking a matrix and calculating a singular value decomposition of that matrix. In the lecture, I broke this process down into 3 steps. In the first step, we need to find the eigenvalues of the Gramian of this matrix. In the second step, we need to use those eigenvalues to find a spectral factorization of this Gramian. And then in the third step, we applied 2 formulas to find the matrix sigma and the matrix U that arise in the factorization. So let's walk through the first step, which is to calculate the eigenvalues of the Gramian of this matrix. Now, keep in mind, eigenvalue calculations in general are quite difficult. So there's no reason to believe that if you write down some random matrix, that the eigenvalues of the Gramian will be particularly easy to calculate. But this example was chosen so that we can do this by hand. So let's jump right in and find our eigenvalues. Our primary tool for finding eigenvalues is the characteristic polynomial of a matrix. So let's look at the characteristic polynomial of the Gramian of this matrix and see if we can't factor it. Before we look at that characteristic polynomial, we need to actually calculate the Gramian. So let's figure out what this matrix is. So we need to take the conjugate transpose of A and then multiply by A. So what is the conjugate transpose of A? Well, A is 4 by 3, so the conjugate transpose should be 3 by 4. So what are the new columns? The new columns are negative 1, 0, 0, negative 1, 2, 2, 0, 0, 0, and then 2, 0, 0. So this is the conjugate transpose of our matrix, and then we're going to multiply by our matrix. Negative 1, 0, 2, 0, 2, 0, 0, and then 0, 2, 0, 0. So that's our matrix A. So when we multiply this 3 by 4 by this 4 by 3, we produce a 3 by 3 matrix. And what are the entries here? So the first entry will be the dot product of negative 1, 0, 2 with itself. So that is 6. The entry to the right, and consequently, because of symmetry, the entry right below this will be the dot product of negative 1, 0, 2 with 0, 2, 0, 0. So that ends up being negative 2. The 1, 3 entry is the dot product of this first row with of A star with the last column of A, which is another negative 2. And so consequently, that's also the 3, 1 position. The 2, 2 position is the dot product of 0, 2, 0, 0 with itself. So we get 4. The 2, 3 position is the dot product of the second row of A star with the third column of A, and that is another 4. And consequently, a 4 goes in the 3, 2 position. And the last missing entry is the 3, 3 position, which is the dot product of 0, 2, 0, 0 with itself, which is 4. So this is our Gramian, and now we wish to calculate the eigenvalues of this Gramian. Before we jump into this calculation, it's worth looking at the matrix and noting a few things. One thing we can see right away is that this Gramian is a rank 2 matrix. The first 2 columns are not multiples of each other, but the third column is equal to the second column. So this forces the matrix to have rank 2. And in fact, we could have predicted this because in our original matrix, the first and second columns are different, but the third column is equal to the second. So now let's look at the characteristic polynomial. So the characteristic polynomial of A star A is what? Well, the notation I like to use is chi sub the matrix, so A star A now of T. And by definition, we're looking at the determinant of the difference between T times the 3 by 3 identity matrix minus the matrix of interest, which now is the Gramian. So what we're doing is we're taking T and subtracting the diagonal and then negating all of the other entries. So the first entry will be t minus 6. Then below we'll get 2 and 2. Then we'll get 2, t minus 4, and then negative 4. Then we get 2, and then negative 4, and then t minus 4. So we want to take this determinant, and then which will give us a degree 3 monic polynomial, and then we want to take that polynomial and factor it. Now, when I'm doing these calculations, I always try to look for some row reductions that make life a little bit easier. One thing that I see right away, and maybe I can highlight this, is, and again, there are lots of ways to go about this, but this is just is how I happen to look at it when I looked at this problem. There's a 2 in the 2, 1 position, and there's also a 2 right below it. So I decided to take the 2 in the 2, 1 position and clear that entry out using the entry right below it. So in other words, I'm suggesting we can do the row operation. Row 2 minus row 3 gets sent to the new row 2. So what happens when we do that? So again, we're taking row 2 here and subtracting the third row. Well, we're not changing the first row, so t minus 6 remains t minus 6. And the whole point of doing this operation is to take this 2 in the 2, 1 position and clear it out, so we get a 0. And then we're not changing row 3. So now we just track all the math. 2 remains the same in the first row, and then now we're taking t minus 4, and then we're subtracting negative 4, and that just leaves us with 1t. We're not changing the third row, so we keep our negative 4. We're not changing the first row, so we keep this 2. And then now we're taking negative 4, and then we're subtracting the quantity t minus 4. Well, when we do this subtraction, we should get negative 4 minus t plus 4, which leaves us with a factor of negative t. And then finally, we're not changing the third row, so we keep our t minus 4. So we've done one row addition, and that row addition doesn't change the determinant. So these the equal signs are correct here. But we've managed to simplify this determinant because now sitting in the second row is a factor of t in each position. And remember, factors or terms factor out of rows and columns actually of determinants. So this t now factors out of the second row. T multiplied by t minus 6, 0, 2, 2, 1, negative 4, 2, negative 1, t minus 4. So the t has now successfully factored out of our matrix. And now this is great because we've eliminated some of the non-constants from our determinant. And now I have a 1 right in the middle of my matrix. And I can maybe use this 1 now to clear out the other 2 entries in the second column. So what we could do now is we can take row 1 and subtract 2 row 2. And then we can take row 3 and add 4 row 2. So let's do the math there. So our factor of t carries over. So now I am changing row 1, and the way I'm changing row 1 is I'm taking row 1 and I'm subtracting 2 times row 2. So t minus 6 minus 2 times 0 doesn't do anything to t minus 6, so I keep that. I'm not changing row 2. And again, we're taking row 3 and we're adding 4 row 2, but 2 plus 4 times 0 is still equal to 2. And the whole purpose of this row operation is to clear out the 2 and the negative 4 from the second column. So my new second column is 0, 1, 0. And then now I have to actually do a little bit of arithmetic. I'm taking 2 here, and I am subtracting 2 times negative 1, which is the same thing as adding 2. So I should end up with a 4 in the upper right-hand corner. And then I'm not changing row 2, so my negative 1 stays the same. And then finally, in the bottom right-hand corner, I'm taking t minus 4, and I'm adding 4 times negative 1, which is the same thing as subtracting 4, which leaves me with t minus 8. So I've now managed to simplify my determinant calculation. And the purpose of doing this determinant calculation is to find the characteristic polynomial of the Gramian of the original matrix. And we've made life quite nice for ourselves, because now in the second column of our determinant, we're looking at 0, 1, 0. So we can expand about this column to reduce this 3 by 3 to a 2 by 2. And 2 by 2 determinants are never that intimidating. So I'm going to switch to a new piece of paper here for quality's sake. And so I'm going to recopy that determinant that we had from the previous line. So we're working with the determinant of, well, we have a t sitting on the outside here. And then we're taking the determinant of t minus 6, 0, 2, and then 0, 1, 0, and then 4, negative 1, t minus 8. Okay, so now we're choosing to do a column 2 expansion of this determinant. So the column 2 expansion says we should weigh by the appropriate sign for the cofactor expansion, which is actually plus minus plus here. So we're really just deleting row 2 and column 2 and taking a determinant of whatever's left over. So we have our factor of t that's carrying over, and now we're multiplying by the determinant of t minus 6, 2, 4, t minus 8. There might be ways to mess around with this determinant. There are a few things that maybe I see here. For example, if I took row 1 and added row 2, it looks like that would reduce this term to t minus 6 plus 2, which would be t minus 4. And then 4 plus t minus 8 would give me a factor of t minus 4, which could then factor out of the first row. In fact, that actually looks like a pretty good idea. So let's go ahead and do that. I think in the notes, I actually multiply these two terms together, t minus 6 times t minus 8 minus 2 times 4, and that gives me a quadratic that we can factor. But since we see a nice trick here, why not use it? So this is t multiplied by, so now what I'm doing is I'm taking row 1 and adding row 2, because I know from looking at this that I will end up with the same term in both entries in the first row. So t minus 6 plus 2 is t minus 4. And then I get a 2 down here. 4 plus t minus 8 is t minus 4. And then I'm left with t minus 8 down here. And so now t minus 4 factors out of the first row. So now I'm left with t times t minus 4. And I'm multiplying by 1, 2, 1, t minus 8. And then now I just need to do one more row reduction. I can take row 2 and then subtract 2 times row 1 to clear out this 2. So I'm now going to clear out this 2 here. So my factor of t and my factor of t minus 4 carry over. And then now when I take row 2 and subtract 2 times row 1, I get 1, 0, 1. And then now I get t minus 8 minus 2, which is t minus 10. And now my 2 by 2 determinant is quite simple because this is an upper triangular matrix. So I need only multiply by the diagonal, or multiply the diagonal entries together to get the determinant, which is just 1 times t minus 10, which is t minus 10. So after a bunch of arithmetic and a little bit of creative thinking, we managed to factor the characteristic polynomial of our 3 by 3 Gramian. And this is almost the conclusion of the first step of calculating the singular value decomposition of our matrix. What we need to do now is interpret this factorization, and then according to the first step, by interpreting this factorization, what we mean is find the positive eigenvalues and then list them in order. So the conclusion now is the eigenvalues of the Gramian of our matrix are lambda 1. So lambda 1 is always chosen as the largest eigenvalue of this matrix, which is 10. And then if 10 had a bigger algebraic multiplicity, we would list it again until we exhaust the algebraic multiplicity. But here the algebraic multiplicity is 1, so we move to the next largest eigenvalue, which is 4. And then in SVD, we ignore the 0 eigenvalue. So there is no lambda 3 in this example, even though there is a third eigenvalue. I guess maybe a more rigorous way to state it is there is a lambda 3, but we won't include that lambda 3 when we find our singular values.